Okay. So on Tuesday, the notes we went over, those were over relative dating. The big thing to remember with relative dating is there are no numbers associated with it. So you don't get a specific age, you get a specific number. You're just talking about, this is older than that, or that is younger than this, or if these are rock layers, you know based on the law of superposition, where it says that the new stuff is on top, the older stuff is further down. If these were rock layers, this rock layer is older than this rock layer. That would be relative dating. If you want numbers, if that's what you're looking for, you need to look into various techniques of absolute dating, where absolute dating has numbers. So that's where you're going to get ages, how old is something, that sort of thing. And there are different ways that you can do that. One way, if all you're interested in is figuring out how old trees are, is by counting tree rings. If you cut down a tree and look at the tree trunk, it will have tree rings. Now, if you're the one that cut it down, you know exactly when you cut it down. And if you count from the outside and you count every ring all the way to the very center, that will tell you how many years that tree has been alive. There are some problems with that. One big one is there are a lot of things that we want to know how old they are that aren't trees. And there are a lot of things that we'd like to know how old they are, and they're a lot older than trees, like rocks and things like that. But trees kind of serve as an example of a way that you can assign a value and determine the age of something. One of the other problems is if you don't cut down the tree, but let's say the tree is just laying in the forest, you don't know when that happened. So you can count to see how old the tree was when it fell over. If you don't know when that happened, then you can't figure out the age of it. And this last little bullet point where it says bristlecone, that's a type of pine tree, a bristlecone pine, and is one of the oldest trees found, and it was 4,600 years old. So from the outside edge to the very center, there were 4,600 tree rings, which is pretty amazing. I mean, it's a really old tree. On this slide, this is just, this shows one of the sequoias or redwoods, which are huge trees. And this is a close-up of some tree rings. And in addition to telling us the age of the tree rings also give scientists kind of a picture of how much moisture was available to those trees as they were growing. If there's a year where there's a lot of water or more water, it will have a wider tree ring than a year where there's not as much water, because more water means the tree can grow more. So you have a wider tree ring. If there's less water, it doesn't grow as much, so it has a much narrower, closer tree ring like the ones on the left. But like I said, one of the problems with this is there are a lot of things that we want to know how old they are, and they aren't trees. They're rocks, and they're much older than trees. So I have a little video clip, and this will kind of introduce some things, and then I'll talk a little bit more about some of them afterwards. So let me pull this up, maybe.
The Earth is 4.565 billion years old, give or take a couple million years or so. How do scientists know that? There's no established in plaque stuck on a cliff somewhere. No, geologists got there thanks to a handful of radioactive elements. With radiometric dating, scientists can put an age on dinosaurs and, yes, even good old Mother Earth. So how do you date a rock? Well, it's going to take some good chemistry. Lots of people have tried to date the Earth. Archbishop James Ussher famously used the Bible and a host of other historical documents to settle on the evening of October 22nd, 4004 BC. He was off by just a little bit. Things started to get more scientific during the Industrial Revolution. Geologists looking at layered rocks realized they were formed from gradual deposition of sand, silt, and other sediment, and that must have taken a long time. Once scientists came around to the idea, they tried some new approaches to deciding its age. Lord Kelvin had an idea to date the Earth by figuring out how much it had cooled down since it was formed. He settled on somewhere between 24 and 40 million years old. Better than Ussher, but Kelvin still didn't come close. One reason why is he didn't know that there was something inside the Earth that was actually keeping it warm: radioactive rocks and minerals. The discovery of radioactivity in 1896 paved the way for radiometric dating, which lets scientists put an accurate age on just about anything, even the planet. To understand how, let's take a closer look at what happens to radioactive elements as they decay. We start with an atom of a radioactive element. Scientists call that the parent atom. When it breaks down, it releases, well, radiation. That transforms it into a whole different element, which scientists call the daughter atom. When you have a whole bunch of radioactive atoms together, the overall rate of decay from parent to daughter is constant. When half of the parents have become daughters, that's called the half-life of that element. That half-life is the key to radiometric dating. By counting up the number of parent atoms of a given element and the number of daughter atoms around it, scientists can figure out how long those atoms have been there. There could be a dinosaur bone, a big trilobite, or some other rocky, really old thing. No, not him. That's better. To get an accurate age for something as old as the Earth, geochemists have to be a little picky about which elements they go out looking for. The parent and the daughter element have to be stable enough that they'll both still be around after billions of years. Otherwise, there'd be nothing to compare. Uranium is a popular choice for dating rocks. It's a radioactive element that's sometimes incorporated into crystals of zircon, a mineral formed as magma cools. Cubic zirconia also provides cheapos with a cop-out engagement ring option. Uranium decays through a series of radioactive elements into a daughter atom, lead. Zircon doesn't incorporate lead while it's forming. That's important because it helps geochemists know that the lead they find in zircon comes from decaying uranium. So when they collect a rock in the field, bring it back to the lab and count the atoms in the zircon crystals, the ratio of lead atoms to uranium atoms in any zircon crystal tells geochemists when that crystal formed. But here's the thing. Geologists have never found pieces of Earth that have been around since the planet was born. Our world is an active place. Rocks are constantly being smashed and melted and reformed, so it's no wonder very little has lasted all that time. The oldest zircon we found is pretty close, somewhere around 4.4 billion years. So why do geochemists say the Earth is even older? Well, scientists arrived at the 4.565 billion years by expanding their dating pool. They used the same radiometric techniques to date meteorites. These space travelers are practically unchanged since the very beginning of our solar system, when they, the Earth, and the other planets formed. Since they don't have to deal with magma and weather and other geology business, the rocks on meteorites are a snapshot of the solar system's early days. Geologists love dating meteorites. You might even call them rock stars. They're like time capsules that crash into the Earth. The minerals in them can be radiometrically dated just like any others. And that, my friends, is how you date a rock. In less than 100 years, scientists went from numbering the Earth's age in thousands of years to billions, all thanks to a handful of elements and the scientists who revealed their secrets. Not that they're satisfied, of course. Geochemists are still fine-tuning their estimates of the age of the Earth and looking for more evidence to support or diminish their theories. But really, the only rock I have my eyes on right now is Dwayne "The Rock" Johnson. That guy's dreamy. Oh, one other thing. Happy National Chemistry.
All right. So nothing from, nothing against the National Chemistry Week, but we don't need that right now. Okay. All right. So when it comes to dating really old things, figuring out how old they are, I've never personally dated the Earth or tried to date the Earth. I'm already married. Sorry, couldn't help it. One of the things that allows us to figure out how old really old things like rocks and the Earth and all that are is the property of radioactive decay. So if there's a radioactive isotope that is unstable, it will give off radiation. Radiation is just a form of energy. It gives off that energy. It also gives off particles from the nucleus, like protons. when that happens, it changes what element it is. So an example we'll talk about is uranium changes to lead. Now it goes through a series of steps where it's different elements, but it eventually ends up being lead because it's giving off energy and giving off proton. Also, radiation and radioactive things are not things that you want to spend time around. It's not good for you. It can make you very sick. I mean, it can cause death. It's not good. With radioactive decay, as mentioned in the video, is something called the half-life. All the half-life is the period of time that it takes for half of the atoms of an element in the sample to become not radioactive. Now, this is kind of a confusing thing. I think one of the parts that makes it confusing is that different elements have different half-lives. So, this element here has a half-life of 100 years. This other one has a half-life of 2 billion years. A different one might have a half-life of 4 seconds. They have different half-lives, but each radioactive isotope, it only has one. That never changes. But if you look at every radioactive isotope that's out there, they're all different ones, all different times, all different periods of time. But each one has their own specific one, and that's it. It doesn't change. So like I said, it's from when the radioactive stuff becomes not radioactive, or when half of it becomes not radioactive. So in this chart, the yellow part is radioactive. You can think of it that way. And we call that the parent material. So that's what you start with. The other kind of bluish, grayish color, whatever that is, the daughter product, it's not radioactive, it's stable, it's not dangerous. So the period of time that it takes for half of the parent material, which is radioactive, to become not radioactive and safe, that's the half-life. So for this, let's say the half-life is 1 hour, just for an easy example. So starting at time 0, starting at time 0, all of this sample is radioactive. Every atom in there is. Now, one half-life, which has been 1 hour for this example, half of it half of the sample is still radioactive. This is not radioactive. Another half-life passes. Of the stuff that was radioactive, now we're at half of that is still radioactive and half is not. Another half-life passes. Of the stuff that was still radioactive, half of it is still radioactive. That half is not. Another half-life passes. Kind of see the pattern. This is still radioactive. That's not radioactive. Another one, another one. So the period of time that the half-life is really doesn't matter so much. It's just that every time that period of time passes, half of what is radioactive is not radioactive anymore. Like I said, it's kind of confusing. You won't have to do a lot with this, so I wouldn't stress over it too much. It's kind of another way to look at it with a pie chart. So if you start at everything radioactive, and then it goes to half, and then a quarter, and then an eighth, And this kind of shows that eventually it'll be zero. None of it will be radioactive eventually, because over time, all these atoms will become safe and stable. One of the things mentioned in the video clip was that uranium changing to lead. So the half-life of uranium is 4.5 billion years, which is pretty much the age of the Earth. So every 4.5 billion years, half of the uranium is not radioactive anymore. So when the Earth first formed, all of the uranium was radioactive, but 4.5 billion years later, only half of it is. Another half-life, and half of that will be radioactive. So scientists can they can compare uranium to lead and look at the ratio and figure out how old it is. So with this one, if there's a rock sample that has equal amounts of uranium and lead, how old is it? Since they're equal, they're 50-50, they're half, that means that the sample is 4.5 billion years, because that's the half-life of it. So the only time that you could have equal parts uranium and equal parts lead is right at the half-life. Now, if there was more uranium than lead, it would be less than 4.5. If there was more lead than uranium, then it would be older than 4.5. So like I said, we won't do a lot with it, just to kind of jump around real fast. But I'll go to this last one. All right, so for this last one, what I would like you to do is use the chat for this. When you put your answer in the chat, don't submit it. Don't click enter, or don't hit enter. Don't post it. And you can send it either to me directly, or you can just post it. But with this problem, after 3 half-lives, how much parent element is there? So using this chart, after 3 half-lives, how much parent element is there? Like I said, put it in the chat, but just don't click enter. I will give you a hint. It's a fraction. It is a fraction. So 3 half-lives, how much parent element is there? So go ahead and post it in 3, 2, 1, and post it. Good. 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 All right, so the answer is 1/8, 1/8. So to get that, so we're looking at 3 half-lives. So since this is 0, 1, 2, 3, so we're looking at this one. So 3 half-lives, how much parent material are we looking at? So we want to figure out how much of the white bar there is. So at 3, going to here where it crosses that line, and we follow that over, and that gives us 1/8. So that's 3 half-lives. 2 half-lives is 1/4. 1 half-life is 1/2, because it's 1 half-life, there's half of it there. At 4, we're at 1/16. And 5, we're at 1/32, way out here. So each time the amount of radioactive stuff gets cut in half. So we're at 1, then we're at 1/2, 1/4, 1/8, 1/16, 1/32. Then we go on out to 1/64, then 1/128th, and then 1/256. Then it just gets smaller and smaller and smaller. we won't have to do a lot with Half-Life. But I would suggest being able to pull some information if you have a graph or a chart similar to this, being able to pull some information about, what's going on in the chart. If you're asked to do that, it might come in handy at some point in the near future. Are there any questions, or does anyone have any slides that I need to go back to?